Alright, we've started recording and I'm going to take you to the practice quiz. And problem number 1. Use notation you've learned in this class using limits to state the vertical and horizontal asymptotes of that picture. So we give about 30 seconds more. Okay, so we would say for the vertical asymptote, it would be the limit as x approaches 1. Now from the left, it's going to positive infinity. From the right, so I could put plus, minus, but since it's going from both sides to positive infinity, we don't have to put either one. Of the function, whatever I call it, let's call it f of x, that is equal to infinity. As x gets closer and closer to 1, the height of the function goes up towards infinity. And then for the horizontal asymptote, that's the vertical asymptote. For the horizontal, it's the limit as x approaches either infinity or negative infinity. Most often we're interested in positive infinity, because very often x is time and time just goes forward. But it could be either one of the function. As we get closer, we get larger and larger inputs, the outputs get closer and closer to a height of 0. And that's how we now state a horizontal asymptote. It's a more inclusive way, doesn't miss things than the way we stated them before we had calculus. So, give me a little feedback on this. Did you need the review on this, or no, or could use a little more review, or whatever. A little feedback would be good. Okay, so it's good to go back to some topics that we did before. Alright, number 2. State the definition of f prime of x, the derivative, and draw a picture that illustrates its graphical meaning. Okay, let me stop you. I'm going to do just the first part right now. F prime of x, by definition, is equal to the limit as h approaches 0, f of x plus h minus f of x over h. Okay, now the last time that we did this with draw a picture that illustrates its graphical meaning, I kind of gave you a head start with that, and this time I didn't. So I'm just going to do this portion of this right now, and then I'm going to give you a little bit more time. Suppose my function f is doing this. Suppose right here is x, and then a little later is x plus h. So let me give you another minute, see if you can get your picture down since I've set things up a little bit. All right, anybody need more time? All right, so directly across from this point is f of x. Directly across from this point is f of x plus h. And then the slope of this line is what we're going to find out. But what the real slope that we're after is the slope of the tangent line, the line that just nicks the curve right here. Now, how am I going to get the slope of this one? Well, its two coordinates are, on this point it's x plus h, f of x plus h. On this point, it's x, f of x. And we've got an extra parentheses around all that. So then the slope, let me get some more space. M, slope of the secant line, is the difference in the f coordinates and the y coordinates. So it's really this height right here between these two heights, divided by the difference in the x coordinates. X plus h minus x just gives you h. So it's the difference between these two values. It's the rise over the run. Now, the slope f prime of x is the same as the slope of the tangent line. And we get the tangent line from the secant by taking the limit as h approaches 0. And then we get the same function up here, and we get the same thing. But when we do that, visually it brings, when h, let's say h becomes half as small, it's over here, then it becomes here, and then we're connecting these two, and you see how we're getting a much better approximation of the red line. The closer we bring the second point to the first point, the closer the blue lines become to the red line. Alright, so give me feedback on this. You could let me know things like, oh, this, when you started the graph, that really helped, or I could do it without that start with the graph, or where you were at in this stuff. I needed this review, or I didn't. all that's helpful. Okay. Let's go to the next one, which is really number 3. Let me remember this. And this is part A underneath it. And this is part B. Alright. If the tangent line to the graph of y equals f of x at x equals 2 passes through these 2 points, then A, find the equation of the line tangent to f at x equal 2, and B, find f of 2. So, it might be a little confusing. Drawing a picture usually helps. Okay, who needs more time? Alright, if no one, we'll go ahead with it. So, I'm going to graph these 2 points. Three over, 5 up, and 6 over, 2 up, no, 2 down, down here, these 2 points, and now, the line tangent to the graph y equal f of it at x equals 2 passes through these 2 points. So, when x is 2, that's what we're really interested in. And now I'm going to have to make this line a bit longer because it doesn't even go directly above 2. Now, the graph of f, I don't know anything about it, except one thing. The tangent line, when x is 2, looks like this. Does this mean, like, could my f be like this? Could my f be something like this? Because here the tangent line would be parallel to that. The tangent line right here is parallel to that. The answer is no. The f can't be like this. It can't be just parallel to it. The tangent line to f is this blue line. So at 2, directly above 2, I come to this. My curve has to pass through this point. It could pass through something like this, so that the tangent line is there. Alright, so actually the tangent line from this line right here, we can find out, let's find the equation of this blue line. First step is to find the slope. So let me go back to blue. So its slope is negative 7/3. And then we need a point. Well, we can take either one of these. So y minus 5 is negative 7/3 x minus 3. Distribute the negative 7/3. Y minus 5 is negative 7/3 x. Minus and minus make plus. The 3's cancel each other out, and I get 7. I add 5 to both sides. Y is equal to negative 7/3 x plus 12. Alright, now that's the equation of the tangent line. And the curve y equals f of x has to touch that tangent line. So when x is 2, we can plug in 2 for the x and figure out what the y coordinate of this point directly is right here. If I plug in 2, I'm going to get y equals negative 14/3 plus 12. Now, 3 goes into 14 4 times, so it's negative 4 2/3. So if I subtract 4, I get 8. Subtract 2/3, I get 7 1/3. So this point is 7 1/3. The height. Right there. It's 2 over and 7 1/3 up. In fact, that's my f of 2. 7 1/3. And then, so I have found the equation of the line tangent to f at x equals 2. It's this one. That's the answer for A. And then for B, I just found it 7 1/3 over here. Alright. Feedback on this would be really good. Tell me if you were really lost, you kind of had certain parts. You might tell me what parts you had, and what parts you found more difficult than others. All of that will help me assist you better in the future. Easy to doubt yourself on this. So let's go back now. Write and these are supposed to be A, B, C, and so on. So this is number 4, and this is A, and this is now from memory. Write all these rules. Don't look them up. And it's kind of interesting to see if you can write them in their abstract format, because it's different than using them. And as we start to think about the final exam, being able to recall these things in their abstract form can be really helpful at times. Alright, so all of these, power rule, product rule, quotient rule, show how the quotient rule comes from the product rule, if you can, and the chain rule. Okay, 30 seconds more. Okay, so there's many ways to write each of these rules. Like the power rule. I could write y equals x to the n, and then y prime equals, and so on. But my favorite is to go d dx. The derivative of x to the n is nx to the n minus 1. And the product rule. And what's crazy about this rule is you need two functions. F of x and g of x. And then it's the first times the derivative of the second plus the second times the derivative of the first. And then quotient rule, the derivative and I'm going to do so I can not just write down the rule but also show how it comes from the product rule. This is the same as the derivative of f times g to the negative 1 power. And remember, if I had just put a little negative 1 above the g, that's notation for inverse function, and we don't mean inverse function. It's g to the negative 1 power, so that's why I put that extra bracket there. Okay. Okay, and then if I use the product rule on this, first times the derivative of the second. And then chain rule. Plus the second times the derivative of the first. And then this is equal to, now this first one, I'm going to put negative f g prime up top and g squared on the bottom, moving that to the denominator, plus f prime is on top and g will move to the denominator. And then I'm going to get common denominators, so I'm going to multiply top and bottom by g. And then I get, now this is the normal way we think of it, bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And there's the quotient rule and how it comes from the product rule. The chain rule in its abstract form. This one is difficult in its abstract form. There are two different formats, and you could have either one of these. But one way to understand, if we're trying to take dy dx, we can introduce a new function u. That's the chain rule, and the du's would cancel out, and you get this. The way we actually execute the chain rule is like this. If you have f of g of x, and you're taking the derivative, you take just the derivative of the outermost, leave the inner the way it is. Then you tag on the derivative of the inner, like this. Alright, now I could use your feedback on this. Was this harder by writing these rules in abstract form? Is it easier to use the rules than to write the rules? Was this helpful to go over these in an abstract form, or is it kind of confusing, especially like the chain rule? Or does it add some more insight? Any kind of feedback would be good. Okay. Let's go, it's renumbered as number 1. Write the rules for taking derivatives of, write the rule for taking derivatives of exponential functions, and then the rule for taking derivative of logarithmic functions. I'll give you a minute on that. So just the number one here, parts A and B. Exponential function, logarithmic function, the general rules. Anybody need more time? Let's go to exponential. Now, I like to write a derivative rule as d dx. The derivative of, and now I can put, the simplest thing I can put here would be e to the x. And the derivative of e to the x is e to the x. But if I want to just write one rule for taking the derivative of all exponential functions, I might want to change it from e to the x to a to the x. And if I did it a to the x, then it would be, the derivative would still be a to the x, but then I tag on ln a as the penalty factor for not having e as the base. Now if I wanted to generalize that even more, so have one rule that does all the exponential functions, is the exponent doesn't have to be x. It could be a function of x. Let's call it u. A to the u. And then I get a to the u ln of a. That's the penalty factor for not having the right base. And if it is the right base of e, it's just 1, and multiplying by 1 doesn't change anything. And then du dx, chain rule, because we could have a function of x. That is the only rule you really have to know to be able to do the derivative of all the exponential functions. Write that. Okay. Now, similarly, for logarithmic functions, the simplest thing I could write would be ln x. The derivative of ln x is 1 over x. To generalize that, instead of ln x, I could write log base a. And then I would get of x would be 1 over x, and then in the denominator would also be ln a, the penalty factor for not necessarily having the right base. If I wanted to generalize that even more, this thing right here doesn't have to be x. It could be a function of x. We'll call it u. The derivative of log base a of u is 1 over u ln a is the penalty factor because I didn't have a base of e, and then du dx for the chain rule. Those are the abstract forms of everything you need to know for taking derivatives of exponential and logarithmic functions. Alright, give me feedback on that. Is that harder than actually doing one of those problems? Or does it make it easier when you look at it this way? A little bit of feedback. All right, let's go. Now we have these two rules to refer to, and do number 2. Now, by the way, if you've had me in other classes, or I might have mentioned this before in this class, one of the strategies that you can use in a test is called the memory dump strategy, in which you have some rules memorized, and the first thing you do when you get handed a test, you ignore the test, and on a blank sheet of paper you write out the memorized rules, and you can practice that beforehand. And so if you had like listed these two things out beforehand, you know, when you're first handed the test, then when you're later doing these problems, you've got that to refer to. And it can take away some of the stress, like, oh, am I going to forget this rule when I really need it? Well, you don't really need it so much at the beginning of the test, and you've already practiced that step, so you just dump it down. All right, so go ahead and do 2A and B. Okay, let me do A, and then I'm going to give you a little more time. So y prime, if I just look back up here, this is a to the u. A is 5, u is cosine x. So the derivative of a to the u is a to the u again. And then ln 5, penalty for not having base e. Then I'm going to have the derivative of the cosine x, which is going to put a negative and a sine x. And then that's going to be it. Let me give it a little bit of time before I do B. All right, anybody need more time? So y prime is, comparing this, a is 3 and the u is everything in the parentheses. So it's 1 over the u times ln 3, penalty factor, times the derivative of the u, which is 28x cubed minus 3, like this. And then I'm done. I'd probably put this 28x cubed minus 3 in place of that 1, make one fraction, but that's it. Alright. That's it for the practice quiz. Give me a little feedback on number 2. where you're at with those. Okay, so sometimes having those abstract rules to refer to can help you keep from forgetting something. All right. Questions on homework. We had one already, number 37, and so let's go here. Okay, and let's look at the directions. Find the critical points. Assume A is non-zero. Alright. So I'm going to rewrite this function before I start as x squared x plus 5 to the 1/2. Now, I can't really distribute that x squared in there. I can't distribute the 1/2 to both of those. Just like x plus 5 squared, we would have to FOIL it out. This 1/2 can't get distributed into each one of those. So to find the critical points, I'm going to have to take the derivative. And I need the product rule. First times the derivative of the second. Now, inside here was not x itself, it's a function of x. So I have to use the chain rule. But when I take the derivative of x plus 5 with respect to x, I just get a 1. So it doesn't change anything, but I like to put that 1 in there to help me remember, and when I look back at it, I can say, oh yeah, I remembered to use the chain rule. So that was first times the derivative of the second, plus the second times the derivative of the first. And then we set this to 0. Now, when I set it to 0, I'm going to rewrite this. This is going to come down to the bottom, and then the 1/2 power is going to go back to being a square root. This 2 will join that. Now, usually I leave these as 1/2 exponents instead of writing the square roots, because if I have to take another derivative, I just have to put it back into that format. But here I'm solving an equation. Solving an equation, I think I like them as a square root. Now, before I start solving this equation, whenever I notice a denominator, I notice what value of the variable causes the denominator to be 0. If x equals -5, then you see this thing to the -1/2 really meant it was in the denominator. F prime of x does not exist. So x equals -5 is a critical point. It's an easy one to overlook. Remember, we call these singular. One of them was called a stationary point, This is called a singular point. Now our textbook doesn't use that terminology of singular points and stuff. Some calculus textbooks do. I like those. I do. Okay. Now we still have to solve this equation. So I gotta swing this whole thing, the first fraction, I'm going to swing the first fraction to the left-hand side. So I'm going to get negative x squared over 2 square root of x plus 5 is equal to 2x square root of x plus 5. And the square root sign should come over both. I should be very careful about that. Now, I'm going to do what's called cross multiplying, which when you can only do it when it's one fraction equals one fraction. When you multiply these two and you multiply those two, you get the same result. So I'm going to get negative x squared times 1 is negative x squared. When I multiply these two together, I get 4x. And then the two square roots multiply together and the square root sign goes away. So this is negative x squared is equal to 4x squared plus 20x. And then I'm going to bring this to this side. So I'm going to add x squared to both sides. Okay, and then I am going to factor out. Okay, I could have brought the 20x, let's say, to the other side and then divided both sides by x, but I would lose the solution if I did that of x equals 0. It's better to factor. And I'm going to get x equals 0, and I'm also going to get x equals negative 4 of my two solutions. So, what are my critical points? So, the instructions were find the critical points. So, finding the critical points is you only have to give the x coordinates. You could give the y coordinates of each point if you want, but it's not necessary. That's it. And a common one that's overlooked is x equals negative 5. Because remember, if something causes the derivative to not exist, that's also a critical point. Is everything clear on 37? Any questions on that? All right. Other questions? Okay. 63 and 64. The instructions are determine the location of the absolute extreme values of f on the given intervals. Alright, so I'm going to do one of these, and then if we have time at the end, I'll come back to do the other one, but I may not have time. So if you've got a preference, I'll go over to the chat channel and look. If you've got a preference, speak now, or else I'll pick one randomly here. 63 or 64. Anybody have a preference? Alright, so then let me We haven't done really any much with the trig ones, so I'm going to pick that one. Okay, so find the absolute extremum. Find the highest point and the lowest point on this curve. Then what I know I'm going to pick on my curve is I'm going to make a table of values, f, x, and f of x, which is just secant of x. And I know I'm going to put negative pi over 4. And I know I'm going to put pi over 4. And let's go ahead and actually plug them in. When I put negative pi over 4, it's right here, the cosine is square root of 2 over 2, which is 1 over square root of 2. And when you flip it over, you get square root of 2. And on this point, you're getting the same value. So, what other points in between? Well, I can't tell until I take the derivative, set the derivative equal to 0. F prime of x, the derivative of secant is secant tangent. Then we set that derivative to be 0. Now when I solve this, I generally solve these equations by rewriting everything. Secant is 1 over cosine. Tangent is sine over cosine. So 0 is equal to sine x over cosine squared x. Now, there are two possibilities. Either the numerator is 0, and then it's the what's called a stationary point for a critical point. But you could also have the denominator be 0, because when the denominator is 0, then f prime does not exist. That's also a critical point. So, if 0 equals sine x, this is a stationary point, where the derivative itself will be 0. That implies, now, where is the sine equal to 0? Let's scroll up to my little unit circle. The sine is 0 only here, because the sine is the y-coordinate. Hold it, no. The sine is the y-coordinate. The sine is 0 here. So that's when, it could also be 0 over here at pi, but pi is not in between negative pi over 4 and pi over 4. So the only one that's in that interval is when x is 0. This implies x is 0. If cosine is equal to 0, now this is what we call a singular point. The derivative does not exist. Okay. Now, singular points, you can remember those is in physics they call these points of singularity, points where mathematics breaks down. And I think I'd mentioned this before too, like if you put, two electrons and you keep pushing them closer and closer together, the amount of force between the two is proportional to the distance, 1 over the distance. And so if the distance becomes 0, in theory you could get an infinite amount of force there. And so our classical mathematics breaks down there because it's vertical asymptote, a singularity point, like that. And we use that same kind of thing when the derivative doesn't exist. Because at points of singularity like that, we can't find the usual kind of stuff like a derivative. And now cosine is 0. Cosine is the x-coordinate. Cosine is 0 up here and up here, but they are not in between negative pi over 2, negative pi over 4, and pi over 4. So it doesn't matter. So this has no solutions. There's no solution in the interval negative pi over 4 to pi over 4. So the only point extra that we need to worry about is x equals 0. We'll put that in here. The secant of 0 is 1 over the cosine of 0. The cosine of 0 is the x-coordinate of this point way over here in the unit circle, so it's 1. So then I would be able to say that my absolute, those are the only 3 points I have to consider. My absolute min occurs at x equals 0. We could also say it, instead of just saying x equals 0, you could say at 0, 1. You can give both the x and the y coordinate. Depends on your preference.
Can you explain again why you got 0? I see that you got, I know because when you plug in 0 for sine of x, you get 0. For cosine of x, you get 1. But can you explain why 0 would be part of the answer?
Why 0 is, alright, because we want only, I'm not sure if this is what you're asking, but I'm going to guess that this is what you're asking. We want only from negative pi over 4 to pi over 4. We want only the angles in this region from here to here. When you solve the sine of x equals 0, you get these 2 points on the far right of the unit circle and on the far left of the unit circle. And that 1 is a solution, so x equals 0 is a valid solution. We keep that one because it's in the region from here to here. When we solve cosine x equals 0, that's when the x-coordinate is 0. We get the upper point of the circle and the lowest point of the circle. But neither of those are between negative pi over 4 and pi over 4. So we say we're not interested in those solutions. So that's why we only include the sine x. Bianca, does that get at what you were asking?
Kind of, but not really.
You want to try again with your question?
Yeah, because for the equation, it's sine of x over cosine x squared. But, never mind.
Alright, perhaps this. When you have 0 and all you have is one fraction on the right hand side, 0 equals a fraction. Something on the top, something on the bottom. The only true solution of that is if the top is 0. The only way a fraction can be 0 is if the numerator is 0. But we also have to consider the case where the denominator is 0. If that denominator is 0, that's what we call a singular point, because this right-hand side is representing the derivative. And if the denominator is 0, then the derivative doesn't exist, and we have to consider that as well. So the only way to solve when 0 equals a fraction, you just set the numerator to 0, and then later you also set the denominator equal to 0. All right, and let's now the absolute max occurs at x. Now this takes too much writing. I'll just write it. The x coordinates. And that would be it. So I have my absolute min and my absolute max. Alright, let's take a break. We'll start again at 12:47. Okay, back to it. Get some more. Okay, we'll start up again, and we're going to 4.3, what derivatives tell us. And that's the title in the textbook, and it's not very descriptive. What really is going to happen in this section is we're going to learn about second derivatives. There's a graphical interpretation that's extremely important for second derivatives, so we're going to figure out today. And there's what's called the first derivative test and the second derivative test, and we'll work on both of those. All right. To get us there, though, I have an activity. So you'll do these in your groups. Number one, what do the following mean about the graph of f? So part A, f of x is positive everywhere. There's a lot of different ways you could say what that means about the graph of f, but I want the very simplest, clearest interpretation of what that means. So you might get a few suggestions, and then as a group you can kind of pick out the one that you like the best. So I'm going to give you a minute for that. Ten more seconds. All right, group 6. F of x is positive everywhere. What does that tell me about the graph of f?
That's saying that the graph of f basically never touches the x-axis. It's always remaining above the x-axis.
Aha! So f is always above x-axis. I can't think of a simpler way to state that. F is always above the x-axis. All right, let's go to part B. F prime of x is positive everywhere. What's the simplest way you could state what that means about the graph of f. Give you a minute in your group. Ten more seconds. All right, group 3, what do you have? If f prime of x is positive everywhere, anybody from group 3?
We just said that the graph increases, that the
F,
function increases.
So we could say f increases. Okay, now, is there another way to state that? Did anybody have another way that makes sense to them?
Or you could say like a positive slope.
Okay. So f is increases or positive slope? Probably increases is a little less technical. So maybe for, non-mathematical reader, and we might even say, defining that, moving from left to right, you're going uphill. If this was a stock market curve, you'd be gaining money. Okay. Now, let's go to C. F prime prime of x is positive everywhere. To understand what this means about f, we have to do it in 2 steps. We first have to make a claim about the graph of f prime, and then make a claim about the graph of f. So, let me give you a minute to mull that over. Ten more seconds. All right, group 2. What's the claim about the graph of f prime?
We put that for f prime, it would be above the x-axis. So if f double prime is
let's look at that.
Okay.
F prime is above the x-axis. So f prime prime is positive everywhere. Does that mean that f prime is above the x-axis?
Oh, okay. No, I was thinking like if the slope of f double prime is positive, that would be if it's positive. So if f double prime is positive everywhere, is that meaning that the slope is positive everywhere, or the actual values are above everywhere?
So, yeah, do you want to change your claim? Or do you want to leave it like this? I
I'm
think this is a
interpreting.
pretty good start. Let's check to see if this is true.
Okay.
Maybe f prime is above the x-axis. All right. To analyze whether this statement is true or not, let me change color here. Let's look at this one again. When f prime is positive everywhere, then you can look at the one that's one derivative less than that. F prime is positive everywhere, then the thing that's one derivative less than that, f, is increasing, or positive slopes. So if we kind of look at it in that direction, we can kind of do the same thing over here. Then if f prime prime is positive everywhere, then the thing that's one derivative less, f prime, is increasing. Now, it's kind of an abstract thing that I'm stating, but you all were able to put that together yourselves. When f prime is positive, that means that f itself had to have been, the instantaneous slopes were always positive, or it was going uphill. F prime prime, how do you get f prime prime? You take f prime and you prime it. So when you're priming this, you're doing that to this function. So you're saying the thing inside here, just like this prime right here was saying the thing inside that prime was increasing, so f prime must be increasing. Now, if f prime is increasing, is that the same as f prime is above the x-axis?
Not quite.
Not quite. It's similar, but not quite. But it was a great
So then-
starting point, though.
I was wondering, does it just loop back to f prime of prime being above the x-axis if f prime is increasing?
That's a good guess. Maybe that will be what we're going to make as our claim about f. Maybe f will be above the x-axis. That's a very reasonable guess given these two here, but it turns out not to be true. We need to now, first of all, is everybody okay with this? Claim about f prime is increasing.
So if I just like to kind of I graphically represented it. So I looked at like maybe the f of x being x cubed, for example.
Okay.
And then I took the derivative, which would be a parabola, and then the derivative of that, which would be a line. And so I guess just looking at the graph, I was seeing that f prime of x was above, I guess, except for at 0. But I'm just wondering, is that the wrong way to look at it? If we're looking at
All right. Well, that's really cool what you did. You said if y is x cubed, then y prime would be 3x squared. And now what we want, though, is something where the second derivative is positive everywhere. Here, the first derivative is positive everywhere, except at 0. So if we notch this up one more, let's, instead of doing it y to the cube, let's do y to the 4th. Y equals x to the 4th, then y prime is 4x cubed y prime prime is 12x squared. Now this y prime prime, when you square something, you always get positive. So this one is positive everywhere except when x is 0. So this would meet the condition. F prime prime is positive everywhere. And what it's saying is that the one before it must have been increasing. And that's totally true. Let me get to my eraser here. Let's go back to...
So I think, yeah, so originally, just to clarify, I think my interpretation probably was wrong because I was thinking we're talking about slopes being positive, but we're actually talking about the value at each f of prime, double prime of x or f prime of x. Is that the distinction?
Actually, you were really, I think you gave a big insight here. So y equals x to the fourth looks like this. 4x to the cubed, 4x cubed looks like this. What do I notice about this curve? It is always increasing. 12x squared is back to looking like this again. So what must be true about f prime? It must have been always increasing. If the second derivative is always positive, then that one must have been always increasing, just like this. All right, now we're going to make a claim about f. And to do this, we have to analyze what it means that f prime is increasing. And for this, I'm going to switch over to my camera. Get a little more light here. We need to look at what it means that f prime is increasing. So I'm going to start with a picture. If here is my f, this is my function f. Now the f primes are, see, this is, if you bought stock in this company, boy, would you be sad. You're a negative slope. But the slope isn't quite so negative here. So are the slopes increasing from there to there as time goes on? Yes, they are, because they're getting less negative. They're going in the positive direction. And eventually you get to where your slope is 0. My slope is, so here's m equals like -4, m equals maybe -1, m equals 0. Now if my slopes are going to be increasing, can I make this curve arch down like this? No. If I make it arch down, I'm going to be going back to negative slopes. I'm at 0. If my slopes are increasing, I have to arch up and give me m equal 1. And then I'm going to keep arching up. M equals 3. What I get when I do this, f prime is increasing as we say that f is concave up. And what does concave up mean? It's kind of a bowl-shaped. Bowl holds water. If it was raining outside, when you have a concave up shape, you're going to get a kind of a bowl that would hold water. You're going to have the opposite case if it's concave down. It would be an upside down bowl, and the bowl wouldn't hold any water over here. So whenever we have derivatives that are increasing, we are always, now let me get a ruler back in just a moment. Okay, so this ruler is telling me what my slopes are. And it was going downhill, losing money. Well, it's got to be losing less money. It's to be increasing. And then finally gets to where it's holding its price steady. That's a stationary point. The derivative is zero. If it stayed that way all the time, the price would stay stationary forever. But it doesn't. It keeps going, increasing, and then we get this. No matter how your graph started, it's always going to, if its f is increasing, let's suppose you were horizontal when you started, f. Now I want to have an increasing. As I move to the right, my slopes have to get larger. And if I do that, it's going to cause this to happen. Now, if you only drew the right-hand side of it, you might wonder, well, hey, wouldn't all the water leak out of the bowl? Well, if the trend had been going further on the left, then we'd say the bowl will hold water. If you get enough of the bowl, I mean, you might only get part of the bowl on this case. So if you are already going up, and then you're moving to the right, you got to increase. Then you're going to get concave up like this. And if you were going down when you started, then as you move to the right, you're going less downward. So, the stock is doing better. It's not decreasing quite so fast. And then you'll get the complete bowl shape like this. All these are pictures that have to be in place if f prime is increasing. And it determines the concavity of the original function. So we're going to come back to here, then make a claim about f. The claim is f is concave up. So, great big new concept, concavity. And it's a really important concept for us as well. All right. Now, let me go to back to here, print screen, insert it back. Oh, let me undo that. We need a little more space first. let's erase this. In an interval where f prime is increasing. Now, if f prime is increasing, that means f prime prime is positive. That's very important. The curve f bends upward. You're always getting steeper and steeper. Called concave upward, which we usually abbreviate to call concave up. And bowl holds water. And the picture looks most like a bowl if we start f decreasing, and then as we move to the right, we gotta tilt the ruler up more and more and more. And then we say where f prime is decreasing. Now this happens when the second derivative is negative. Then f bends downward. And it would look like this. Now this, we'll see the complete picture if f was increasing. It was a stock that was increasing in price. But then all of a sudden it's not doing quite as good. It's not increasing quite as much. The ruler keeps turning down. The slopes are getting worse and worse. And as time goes forward, it's even getting worse. This is downward, called concave downward. And bowl does not hold water. Okay, the big point that's kind of makes this understandable is this link between f prime increasing is the same as f prime prime being positive. F prime decreasing is the same as f prime prime being negative. And all right, now we have a new way to look at some common graphs. Let's put this in here. It's more space. So, let me draw a general picture of a graph. XY coordinate system. I'm going to go from this point to this point. Clearly, my function is increasing if I go from this point to this point. And I can make it so that it's increasing the whole way, but there are two different ways that I could make it increase from there to there. One where a trend that's getting better and better, and another on a trend where it's getting worse and worse. Suppose this is a stock price. So, let me show you. This is the trend where things are getting better and better. It was increasing at kind of a moderate rate, but as we moved along, it kept increasing faster and faster, concave upward. Versus, it could have been that things had been going fantastic, and now things are slowing down. It's still increasing, but not increasing as fast as possible. See, both would be ways to have it always be increasing from this point to this point, but which way you do it makes a really big difference. This is concave up, while this is a concave down way of increasing from this point to this point. I'm not going to print screen that because that was all verbal. But everybody getting the idea here? Any questions? All right. Let's look. Another thing that we're kind of used to doing is looking at situations like this. That's good enough. Well, let's come down here. All right. Suppose this was a situation of X was dollars spent on advertising, and this was sales. All right. What calculus tends to be really interested in is these things. And they're easy to find. If this was my function f, I can find these x coordinates here, here, and here. And you just did that in the last exercise that you did. You can find these x coordinates by just taking f prime of x, setting f prime equal to 0, find all the x that satisfy that equation, and that instantly tells you what these points are. And these points have a special name. What are the names of these points? Turning points. We called them turning points in pre-calculus. Now we have another name for them as well.
Inflection.
You're ahead of me on the inflection. We're going to get to that in a minute. These are called what right now?
Those are our critical points.
Critical points. That's right. And we're good anticipation with inflection. We're going to be getting to inflection points in a minute. These 3 points are, let's call them A, B, C. These are our critical points. We called them turning points in pre-calculus, where we turned from increasing to decreasing or vice versa. All right. Now, what we're going to focus on right now in this section is, and it's usually about halfway between critical points. Take these two critical points, go approximately halfway between them, here, this, and let's do it again between these two critical points. Approximately halfway between them, here. These are going to be what we call inflection points. Or the x-coordinates of the inflection points. Technically those are the points, but we often just refer to the x-coordinates of those. And what happens at inflection points is that you change concavity. Notice here the entire curve is concave down. Here the entire curve is concave up. Back here it's concave down. And let me point out that if we were dividing the world up by critical points, you would get this region, which is increasing, the next region would be decreasing. See how inflection points divides the graph up into regions by increasing and decreasing. When, if you own stock in this company, when you're happy, when you're sad, when you're happy, when you're sad.
Did you mean critical points or did
I say, yeah, I said the wrong word probably. So the critical points divide up the world into intervals of increasing and decreasing. Inflection points divide up the world into intervals of concave up and concave down. There's a lot in this. Any questions? Let me print screen here.
So for the inflection points, like it looks like are we at zeros then for our second derivative?
That is let's put this in here. Very good point. Good anticipation. How did we find the critical points? You set f prime of x equal to 0 and solve for x. That tells you all the critical points. For the inflection points, inflection has to do with the second derivative. You set f prime x equal to 0 and then solve for x. Now, why is it that you set the second derivative equal to 0 to find your inflection points? Well, we know the second derivative is positive everywhere in this interval. When it's concave up, the second derivative is positive. We know the second derivative is negative everywhere it's concave down. So if it went from positive to negative, what must it have gone through? 0. And 0 must be that place where it transitions. Just like slopes were positive, slopes were negative. It had to go through a place where the slope was 0. That's the critical point. Similar thing happens with concavity. Critical points, though, you can look at the graph and instantly find them. Inflection points are usually not so intuitive. You can't look at the graph and instantly find them. What I usually do is I find my critical points first and then look approximately halfway between and see if it makes sense to call that a inflection point in that. All right, give me a little feedback. Tell me if this has been a little bit information overload, or you're doing good. Where are you at with a lot of new information here today? Okay. Thanks for your honest responses. All right. Now, I think I got that picture. Yes, that's my picture, so we're all set. Let's look at a problem. Before we look at a problem, let me come over to here and I'm going to explain a couple things. All right, so concavity and inflection points. This is just from the textbook. It's defining what concave up, concave down is. Again, if f prime is increasing, then we're concave up, but f prime is increasing is the same as f prime prime being positive. Okay. And then here's the test for concavity. If f prime prime is greater than 0, then it's concave up. Second derivative is negative, then we're concave down. If C is a point at which it changes sign, then it's an inflection point. And then the first and second derivative tests. Let me explain what these are. You can easily find, from setting f prime of x equal to 0, you can find all the critical points. But suppose you find the critical points. You find 3 and 5 are critical points on a function. But you don't have a graph to look at. How can I tell if 3 is a local max or a local min? Perhaps it's neither. To test whether a critical point is a local max or local min, you can use either the first derivative test or the second derivative test. Now, you don't need either of these tests if you have the graph, because you just look at it and say, oh yeah, that's the highest point. So these are just helpful things if you don't have a graph available. Now, what we're going to do is we're going to be acting as if we don't have graphs available. And we're going to learn how to graph functions without using technology. Because in the act of limiting ourselves and restricting ourselves to this, we'll find that, oh, you really have to know your calculus to be able to do this. So it's a good reinforcing of the calculus understanding. All right. Now, I'll come back to these first and second derivative tests in the context of this example. So let's go to this example. And example. F of x is 2x cubed minus 3x squared minus 12x. And find, first of all, A. Find where f is increasing and where it's decreasing. Now, from the picture that we looked at just a little while ago, let's come back up to here. Notice increasing and decreasing intervals were separated by these blue lines. But these blue lines were the critical points. The critical points divide the graph up into regions of increasing and decreasing. So all I have to do to find where it's increasing and decreasing, I take f prime of x. I get 6x squared minus 6x minus 12. I set this equal to 0. Now I'm going to factor out a 6. I'm going to solve this by factoring it. I'm going to move kind of fast because we don't have much time left. Two things multiply to be negative, so one's positive, one's negative. I want the larger one negative, so my middle term is negative. So then x equals negative 1 and x equals 2 are the critical points. Okay. Now, I wonder if x equals negative 1 is going to be a local max or a local min. And same thing with x equals 2. Whether that's going to be a local max or min. And this will get revealed when I do find out where f is increasing and where it's decreasing. So it's kind of like working in the dark. We're not going to let ourselves make a picture and look at the picture. So instead, we're going to make a little table of values. So my table is going to be intervals, and I'm going to write kind of smallish. Let's see. Now I'm going to do it down here. Intervals. And now, if I have a number line, and I have negative 1 and 2, it divides my number line into these three regions. So those are my intervals. Negative infinity to negative 1. The next one is from negative 1 to 2. And the next interval is from 2 to infinity. And what I'm going to look at is we're trying to find out where f is increasing, where it's decreasing. That information has to do with the derivative. The sine of f prime of x. Now, if f prime of x is positive, that will tell me something. We must be increasing, and so on. So, if I have a point anywhere between negative infinity and negative 1, and I plug it into my f prime of x. Now, I can plug it into this format for f prime of x, this format, or this format. Any of these. Suppose I take negative 1,000 for for x. Well, this is going to be the dominant term. So I can tell that I'm going to get a positive. So I'm just interested in whether it's positive or negative. If I'd have plugged negative 1,000 down in this format, I would have gotten a negative times a negative, making positive. Now, if I take any point between negative 1 and 2 and plug it in. Now, a point between negative 1 and 2 is 0. If I plug in 0, the easiest place to plug in 0 is back up here, because it zeroes out those two, and I get a negative 12, so I can tell the sign of f prime in that interval is negative. If I plugged it in down here, if I plugged in 0, I'd get a positive times a negative, which is negative. And then, if I pick any large number up here, 1,000,000, well, this is going to be the dominant term. I'm going to get positive, or a positive times a positive. It's positive. Now I'm going to make a conclusion about f. What must be true about f if the derivative is positive in that region? F must be, is it true that f must be above the x-axis? Or what must be true about f? It must be increasing. That's what a positive slope means. And this one is decreasing, and this it's increasing. And remember I said, I think I could tell. I'd be very curious as to whether x equals negative 1 is a local max or local min, and x equals 2, whether that's a local max or local min. If f is increasing in this interval, and then decreasing in this interval, and then increasing over in this interval, you can see that negative 1 is dividing these two intervals up. And negative 1 must be a local max. So I would say local max at x equals negative 1, and then local min at x equals 2, because that's clearly the bottom of a valley right over that. And this idea, now by the way, when you have the homework problems and it says find where f is increasing and where it's decreasing, you can just give me a table and you don't need to re-summarize. You don't need to state, oh, it's increasing. I could force you guys to state this again. It's increasing, and then give me the intervals, negative infinity to negative 1, union to infinity, and decreasing from negative 1 to 2. That would be your formal answer, and that's what you'll see in the back of the book. But I will accept it as all you give me is this chart, because that has all the information. It tells me where it's increasing, where it's decreasing. It's all right there. Okay? And if you make these little tiny little loops in here, you can also find out where you have a local max, where you have a local min. Now, this idea that we just did at the bottom, which is when it was changing from increasing to decreasing, you must have had a local max. That's what's called the first derivative test. So let's come back to here, and first derivative test. And the first derivative test is incredibly obvious if you have a picture. When it's in words, it's hard to figure out. But basically, let's look at this first dotted thing. It says if f prime changes sign from positive to negative as x increases through c, then f has a local maximum at c. So if f prime changes from positive to negative as we increase, and see that that's exactly what's happening here. As we're coming here, as it's positive to negative, then we're increasing to decreasing, so it must have been a local max. That's all that this is saying. F prime changes from positive to negative, then you must have a, and if f changes from negative to positive, you had a local min. We went from negative to positive, so right in between must have been at 2, the local min. So that's the first derivative test. And there's another test called the second derivative test, which is faster. Well, let's go. Suppose you didn't have time to make this chart, and you wanted to very, very quickly find out which one of these use second derivative test. Derivative test. To find local max, min. To find out if x equals -1 is local max or local min. Same thing with x equals 2. To do the second derivative test, super easy. We've already found f prime of x. To find f prime prime of x, you take the second derivative, or you take the derivative of this derivative. So this becomes 12x minus 6. Then we take f prime prime and we plug in our critical points. If you plug in -1 into f prime prime, I'm going to get -18. The 18 isn't the important. That it's negative is what's important. F prime prime of -1, just find out if you get a positive number or a negative number. Now, it is negative. What does this mean when f prime prime is negative? Well, we know two things about x equals -1 now. We know that at x equals -1, since it's a critical point, the slope of f is 0. So it's got a horizontal tangent line. We also know that it's concave down. We are concave down since we got a negative answer at x equals -1. So I'm going to draw a little tiny picture. If we're concave down with a horizontal tangent line, must we be a local max or local min? We must be a local max. Thus, x equals -1 is a local max. And that totally agrees with what we'd written down before. At -1, we're at a local max. F prime prime, 2, we plug in 2 into here. I'm going to get 24 minus 6, which is 18, which is positive. I don't care what the number is, I care that it's positive. We are concave up. We have a horizontal tangent line and we're concave up. They must be x equals 2 is a local min. The second derivative test is the quick, fast way to find out whether you have a local max or local min if you don't have a graph to refer to. Alright, so that finishes up our section, the homework. Yeah, 4.3. And are there any questions? There were some questions before about whether you had to do both parts of 4.1. I hope you got that clear. Yes, you have to do both parts. Any questions before we go? Alright, we'll stop here. And I'm going to remember even to stop the video.